You can tell this is an important page because we're on our third video for this one page. So it's important material, but it's difficult material as well. Let's review that we've been talking about the Michaelis-Menten plot. Shown in green, especially the dots, that's the actual data that you could collect in a lab. Then we use the plot, the Michaelis-Menten plot of velocity versus substrate to determine two really important parameters that help us understand how the enzyme and the substrate interact with each other. First of all, we have the Vmax. That's going to be higher or lower, and that tells us something about the speed of the chemistry. That is, the chemical reaction that happens to convert substrate to product in the enzyme active site. So we got to return to that in a minute because that's not quite true. Second of all, though, we had the Km, and that's going to be determining how far left and right we shift. Higher or lower in the Km tells us something about substrate binding affinity. Tighter is going to be lower, and weaker binding is going to be higher for the Km. Now, that's not quite exactly true either. That's why we need to follow up on this page. Let's start with Km. And what I want to do is go down and tell you that Km is sometimes what we would call an affinity constant. Affinity just means sticky. How sticky is it? Does it stick real tight or not so tight? And again, that's all about binding. But what I have to tell you is that it's really a pseudo affinity constant. What does that mean? It means a kind of, sort of affinity constant. It's not a perfect affinity constant. There's some complexities here that I don't want to get into, but I would be remiss if I didn't point out that it's of how tight the substrate binds to the active site. That's all I want to say about that. But I want to spend more time talking about the Vmax. We said above that the Vmax is really the height of this curve where it tangents out, and that tells you something about the chemistry. Now, the problem is that Vmax is not a true constant. You know how constants are. You can look them up in a textbook. If I said to you, what's the melting point of water, you could look that up in a textbook and you'd find that it's 0 degrees Celsius. It's always 0 degrees Celsius. But the Vmax is not a kind of a constant that you can look up in a textbook because it changes depending on the experimental conditions. To help you understand this, I want to do a little thought experiment. Let's say you came into the lab and you did the Michaelis-Menten plot as we have shown here for a particular reaction between an enzyme and a substrate. And let's say you ended up seeing a value where it leveled off of 30 micromole per second. I'll just make up some numbers. And let's say I came into the lab and I did the same experiment and I ended up with a different set of numbers. And let's say mine leveled off at down here at 15 micromole per second. You don't need to write those numbers down. These are just illustrations. Now, it turns out that that's not a problem. If you do the experiment and you get one number and I get an experiment, I get a different number. And the reason it's not a problem is because Vmax is not a true constant. Now, pause for a second and think, what could we have done differently, you and I, that would give us different Vmaxes? Can you think of an experimental condition that might have caused that? Pause for a second and think that through. Okay, the answer to that question is this kind of a situation can come about if we use different amounts of enzyme. Let's say I did my experiment with 1 micromole of enzyme, and you did yours with 2 micromole of enzyme. Remember, the Vmax occurs when we have saturation of the enzyme by substrate. So if you have twice as much enzyme, you're going to have twice as much velocity maximum. So how can we handle this in a fashion that gives us a true constant that describes the speed of the chemistry? Well, It's pretty easy. Let's go down to the bottom of the page and talk about this last one. It's called kcat. And kcat is actually also called the catalytic constant, and it's very easy to calculate. We simply take the Vmax and we divide by the amount of enzyme. Now, take a look at what we have above. If we took your Vmax at 30 micromole per second and divided by 2 micromole, we'd end up with 15. If we took mine and it was 15 micromole per second and we divided by 1, we'd end up with 15. We'd end up with the same number. So we are essentially normalizing our experiments for what's different about them, and that is the amount of enzyme we add. Now notice when we divided through by micromole of enzyme, we're left with strange units. The units are actually 1 per second, or just per second, or we sometimes call it seconds to the minus 1. And that is actually a useful unit because it tells us something more about the catalytic constant, kcat. Kcat is also called the turnover number, and we're going to finish off by writing the definition of this, which is a very useful thing. The turnover number is the number of substrate molecules turned into product molecules per unit of time, in this case second. And here's the main part, per enzyme active site. Now understand what I just said. Number of substrates turned into product per unit time, that's velocity. But if we divide by enzyme, then we actually get the number of substrates turned to product for each active site. And like I said, that's extremely useful. What we're basically saying is that if you had one enzyme molecule, how many substrates can be converted to product in its active site per unit time. Now, this number, turnover number, can be low, like it could be in our case, we said 1 per second. Or it can be extremely high. It could be 100 per second, that's very common. It could be 1,000 per second. It could be 100,000 per second. It could be millions per second. And just think about that for a second. A turnover number of 1,000,000 per second is one enzyme doing a million reactions in a row in 1 second. That tells you the power of enzymes. They're able to make reactions speed up very fast. Okay, to finish up, kcat is the true constant that describes chemistry or catalysis. And we get that from Vmax, which comes from the Michaelis-Menten plot. That's it.